Last time we talked about fracture toughness, and we defined our fracture toughness equation. And we basically said that when the stress intensity K, given by this quantity here, is greater than the fracture toughness of our sample, then we have a fast fracture. And that's our criteria. We're going to need to take a little bit closer look at this fracture toughness value and ask what is the appropriate number to use and what way do we test our sample for this toughness value. So first, there's three modes of fracture. There's a mode 1, which is in tension, a mode 2, a sliding and shear, and a mode 3, a tearing shear. These all will open a crack and cause fracture. The worst case is the mode 1 in tension. And so this is the one that we will use for all of our design criteria. We will assume the worst case. So instead of case C, we will denote this by calling this K1C. All right, so K1C then is our fracture toughness property of our material. And the left side here, we have the stress intensity. And again, when this right side is greater than the K1C of our material, then we have fracture. All right, and then the K1C as well, we're going to do this in a plane strain condition, which basically says that our crack size, A, is small compared to the width of the sample, okay, whether that is an internal crack or whether that is a surface crack. A is going to be much smaller than the width of the sample. So what that's really doing is saying that this crack and the stress fields around the crack don't extend to this free surface of the sample. They don't interact with that surface. And so this gives us a plane strain condition. So that's how we would measure K1C. All right, I've got 3 slides here for you that are basically for your reference when working on problems. They give you the geometry, for example, a center cracked plate in tension. They show you the definition of A here, that's the half width, half length of the internal crack. And they define some other parameters like B, which is the half width of the sample, and H here for the height, the location of the crack, the thickness here as well. And so you can use that when there's an applied load P on the sample to first find the stress. I mean, this is our standard definition. This is our force that's applied over the cross-sectional area, which now is 2 times B times T. And more importantly, they're defining for us in this chart the value of Y that goes into this stress intensity equation. So I haven't really talked about this yet, but Y is just a geometric factor, and it takes into account whether this crack A is interacting with the free surfaces. So it's a function of A relative to B, the width of the sample. Okay, so as long as A over B is less than about 0.4, then Y is equal to approximately 1. So most of the cases we will do, that'll be the case that we're in. But if we do have a case where the A is large compared to B, and the ratio A over B is greater than 0.4, then we can go ahead and plug that ratio in to this equation and calculate Y, the geometric factor, and that's what's actually shown plotted here. So all of our information is on this one sheet for this center crack plate. We also have one for the surface crack. And again, you can see that the crack length for the surface, the full length there is A. Otherwise, this looks a lot like the previous sheet, except now our criteria is the ratio of A over B has to be less than or equal to 0.3, and here we would assume a value of 1.12 instead of 1. Okay, these are all experimentally determined values. All right, and if we had a crack in bending, like shown here, then this would help you with all the geometry, of course, shown, but it gives you the stress then that's on this crack based on the bending moment. It gives you the A over B stability ratio again, where we can assume a 1.12 value. Otherwise, we have to go ahead and put it into this equation to find y, where beta now, instead of just being the ratio a over b, is pi a over 2b. So let's go ahead and take a look at an example. So let's say we have a center crack plate. So that's going to be that first sheet that we looked at of a 2024 T3 aluminum alloy. So this piece allows us to take a look in the text and look up the value for K1C. So it comes from knowing what the material is. Okay? Again, K1C is the material property. So that's a given. Our sample has dimensions, B equals 50, T equals 5, and it's subject to a tensile force of 50 kilonewtons. And we want to know, what is the factor of safety against brittle fracture if the crack length is 10 millimeters versus B, a crack length that is 30 millimeters. So since K, the stress intensity, is a measure of the severity of the crack situation, and K1C is a measure of a material's resistance to fracture, then the safety factor can be defined as simply K1C divided by K. So how is our stress intensity relative to our fracture toughness value? Remember, if the stress intensity K is greater than K1C, that's the case for fracture. All right, so let's go ahead and we'll evaluate first what this value K is for the stress intensity. And then we're going to need the stress first that's being applied. So if we go back to the center crack plate equation, you can see they've given us B here. We've got A, we've got thickness T. So the first thing we're going to do is find the stress. So load divided by the cross-sectional area, 2B times T. All right, so we get our stress value out of 100 megapascals. And then for the case of A equals 10 millimeters, we can go and take a look at the ratio of A over B, and we get 0.2. And on that same sheet that we looked at, we had that if this ratio is less than 0.4, then Y is equal to 1. So in this case, we can go ahead and give Y the value of 1. We just calculated the 100 megapascal value, and our crack length A is equal to 10 millimeters. So our stress intensity is 17.7 megapascal square root meter, which we compare then directly with the fracture toughness of our material, and we get a factor of safety of 2.5. So our stress intensity that our sample is seeing is 2.5 times less than the toughness of the material. So if we go through this again now for the case of A equals 30 millimeters, again, we'll find the ratio A over B. We get 0.6. Now this is greater than the 0.4 ratio. We need to use the value of 1 for Y. So we'll go ahead and use this equation here for Y. Let's go back and check. Right. So we're looking at this equation. All right, there we are. And we go ahead and plug in this alpha, which is the A over B ratio of 0.6. And we calculate our geometric parameter Y is 1.3. So now we can go ahead and calculate that stress intensity again with our new geometric factor. Our crack length being now 30 millimeters. And we get 39.7 megapascal square root meter. Now, technically, that is less than the fracture toughness. So in terms of a test or something, you could say that the sample does not fracture because we're not exceeding the 44. In practice, you would never want to have a design reach that close to the toughness of a material, especially since there's a lot of variability in these toughness numbers. And so likely this would fail for many samples. And so this is really not a good 1.1 safety factor. The other thing we should point out here is that we're at 100 megapascal stress. that's being applied. Now, something like the yield strength of this material is 345 megapascals. So this fracture that's occurring is well below the yield strength of the material. Okay, so sometimes the yield strength isn't really the important parameter, but in fact, fracture toughness becomes much more important. All right,